This is part 2 of the airfoil section of Aeronautical Engineering. As we said in part 1, we left off talking about the graph on page 5. Shows that the center of pressure of a NACA 2312 wing is at about 27% chord at high angles of attack. Okay, between 12 to 16, 20 degrees angle of attack. There's the center of pressure. It's at 27%. We know that because it's 70% of the way from that line to that line, the 20 line to the 30 line. But at lower angles of attack, let's see, like about 3 degrees. See, there's 0, there's 4. That line halfway between them is 2. So let's go between the 2 and the 3. We go up here. See, our center of pressure line is this little one that's kind of light. It's hard to see. It's not this thick lift over drag line. It's this one right here. Okay, if we go up from 3 degrees till we intersect this center of pressure line, and we go over here to the left, we can see that it's halfway between the 30 and the 40. So the center of pressure would be at 35% of the chord. Okay, what do we say here? The graph on page 5 shows that the center of pressure of a NACA 2312 wing is at about 27% chord at high angles of attack, 12 to 20 degrees, but moves back to 40 to 50% chord when the angle of attack is close to 0 degrees. In other words, if this is your wing and you've got a slight angle of attack, the center of pressure is going to be kind of toward the back, but if you increase the angle of attack, it's going to move forward. Back 40 to 50%, forward to 27%, according to our graph. Okay, as you can see, the angle of attack increases and the lift coefficient increases. Let's see. Yeah, see here, angle of attack is 0, 4, 8, 12. As the angle of attack increases, the lift coefficient also increases. This is the lift coefficient line. And you read the numbers over here. See, at this angle of attack, 8 degrees, you go up here, the lift coefficient would be between that line and that line, so somewhere between 0.7 and 0.8. Okay. The aerodynamic center is an imaginary point that is always forward of the center of pressure. The distance between the center of pressure and the aerodynamic center times the coefficient of lift at each position is a constant. In other words, at a low angle of attack, like 3 degrees, when the center of pressure is at 35% chord, the coefficient of lift is 0.35. Okay, let's see where we got that from. 3 degrees. Okay, there's 3 degrees. Okay, when the center of pressure is at 35% chord, okay, follow our 3 degree line up to there, to that center pressure line, go over here, see 35% chord. The coefficient of lift is 0.35. Let's see that. Go up the 3 degree spot here to the coefficient of lift curve, and it intersects right there, but we go over here to read it. It's about halfway between that line and that line, so halfway between the 0.3 and the 0.4. That's how we got that 0.35. But at a high angle of attack, like 18 degrees, okay, see there's 8, there's 16, there's 20, so 18 would be halfway between the two. At high angle of attack, like 18 degrees, the center of pressure is at 27% chord, and the coefficient of lift is 1.44. Let's look that up. Okay, 18 degrees right there. Center of pressure, yep, there it is right there. Most of the way between the 20 and the 30, so it's at 27% chord. And the coefficient of lift 1.44. Let's look that over. Okay, go up our 18 degree line until we intersect our coefficient of lift curve. And it's about 40% of the way up from that line to that line. 40% of the way between 1.4 and 1.5. So let's call it 1.44. It's our coefficient of lift for this NACA 2312 at 18 degrees angle of attack. So the aerodynamic center would be about 24% chord. Because 27 minus 24, okay, 27% chord is where the center of pressure is. But our aerodynamic center is at 24% chord. It's a little ahead of it. So the distance between our center of pressure and our aerodynamic center times our coefficient of lift should approximately equal, okay, this is at the high angle of attack. Center of pressure is forward at 27%. This is at the 18-degree angle of attack. Okay, remember our coefficient of lift is 1.44 at 18 degrees. Now we're comparing that to our 3-degree angle of attack, where the center of pressure moved up to 35% chord, but yet our aerodynamic center stays at the same point at 24% chord. So the distance between where our center of pressure is and where our aerodynamic center is greater in this case, but yet it's multiplied by a smaller number, 0.35. That's what our coefficient of lift is at the small angle of attack. Now, if you crunch the numbers, you'll see that that minus that times that is approximately equal to that minus that times that. So this is how we define an aerodynamic center, as the point at which the pitching moments are constant. The center of pressure changes its position. This aerodynamic center doesn't. And the distance between the two times the coefficient of lift is a constant, or relatively a constant. Okay, this wavy equal sign right there means approximately equal to. You know, straight lines means equal. If we want to know exactly where the aerodynamic center is, we can call it X. See this 24? We assumed our aerodynamic center was at 24% of the way back from the leading edge. Well, instead of writing 24 and saying approximately equal, let's figure out exactly where it is. Instead of saying 27 minus 24, we'll just say 27, or 27 minus 24, we'll say 27 minus X. We'll call the position of our aerodynamic center X. Okay, so 27 minus X times 1.44 is equal to 35 minus, we're going to call it X now, times 0.35. Okay, how do you figure this out? Well, something minus something times something is the first something times that something. 27 times 1.44 equals 38.88, minus that something times there, so minus X times 1.44 is minus 1.44X, equals, let's multiply this one out, 35 times 0.35 is 12.25, minus X times 0.35 is minus 0.35X. So we have that number minus that much X equals that number minus that much X. Well, anytime you have an equation, you can add things to both sides of the equation. You can subtract things from both sides of the equation. You can multiply each side of the equation. As long as you treat one side of this equation the same way you treat the other side of that equation, it'll still be an equation. In other words, it'll still be the same. If you start out with 2 apples equals 2 apples, you add an orange to each side, you have 2 apples plus an orange equals 2 apples plus an orange. You divide each by 2, you have 2 apples plus an orange divided by 2, which would be an apple and a half an orange. You'd still have an apple and a half an orange there. Anything you do to one side of the equation, as long as you do the same to the other side, they stay equal. So what we're going to do is we're going to subtract 12.25 from each side of the equation. Then we're going to add 1.44x to each side of the equation. So 38.88 minus 12.25 is equal to 26.63. Okay, minus 1.44x plus 1.44x leaves us with 0x. So this left side of the equation just has 26.63. Now let's do the same thing to the right side that we did to the left side. We subtract 12.25, so 12.25 minus 12.25 is 0. Okay, and we add 1.44x, so we have minus 0.35x plus 1.44x equals 1.09x. So 26.63 equals 1.09x. So let's figure out what x is. Let's divide each side of this equation by 1.09. 26.63 divided by 1.09 is 24.43. So that would be exactly where our aerodynamic center would be, at between 24 and 25% of the chord, between 24 and 25% of the distance from the leading point of the wing to the trailing point of the wing. Okay, I guess that's enough lesson for now. That's lesson 2. We'll discuss this more during lesson 3, or part 3 of the airfoil sections of aeronautical engineering.